Hello students. Welcome back to class. Today, we are going to explore a new topic, electromagnetic field. But before we get started, let's quickly recap what we covered in our last lesson. In our last class, we explored two major concepts. First, we learned that there is an invisible magnetic field surrounding the Earth, which affects magnetic materials and compasses. When you bring a compass or a magnet anywhere on Earth, it interacts with this magnetic field. This is why a compass needle always turns to point in a specific direction. It is responding to the Earth's magnetic field. Second, we discussed that the magnetic force on a moving charge, it is calculated using the formula F equals Q times V times B times sin theta. This means the magnetic force is equal to the charge multiplied by the velocity, multiplied by the magnetic field strength, and then multiplied by the sine of the angle between the velocity and the magnetic field. Today's objectives is to explore the concept of electromagnetic field, an interaction between magnetic field and currents. Let's explore the fascinating world of electromagnetic fields. An electromagnetic field is a physical field produced by the interaction of electric and magnetic forces. The electric field is generated by stationary charges, while the magnetic field is produced by moving charges. The equation is given by the force F, acting on a charged particle Q, moving with velocity V, in an electric field E, and magnetic field B. Did you know that a wire carrying current can actually move when placed in a magnetic field? Let's explore how and why this happens through a simple experiment. Experiment setup. Imagine we place a copper rod, which acts like a wire, across two metal rails. These rails are inside a horseshoe magnet, which creates a magnetic field between its poles. Now, we pass an electric current through the rod. What happens? As soon as the current flows, the copper rod moves. This shows that a mechanical force is acting on the rod. The rod moves because the magnetic field interacts with the electric current. You're making progress, keep it up. Fleming's left-hand rule and right-hand rule are fundamental principles in magnetism and electromagnetism, introduced by John Ambrose Fleming in the late 19th century. These rules serve as simple tools to determine the direction of electric current in a generator or the direction of motion in an electric motor. It is important to note that they do not provide the magnitude of the quantities involved. Instead, they help identify the direction of any one of the three parameters, magnetic field, current, or force, when the directions of the other two are known. Fleming's right-hand rule states that if you stretch out the thumb, forefinger, and middle finger of your right hand so that they are all at right angles to one another, then the thumb indicates the direction of the motion of the conductor. The forefinger shows the direction of the magnetic field, and the middle finger points in the direction of the induced current. This rule helps determine the direction of induced current in a conductor moving within a magnetic field. On the other hand, Fleming's left-hand rule states that if you stretch out the thumb, forefinger, and middle finger of your left hand so that they are all at right angles to each other, then the thumb indicates the direction of the force or motion acting on the conductor. The forefinger shows the direction of the magnetic field, and the middle finger represents the direction of the electric current. Remember, learning is a journey, not a destination. Let's talk about solenoid. A solenoid is a coil of wire, usually wrapped in many tight loops. When an electric current flows through the solenoid, it creates a magnetic field similar to that of a bar magnet, with a north and south pole. It has a north pole and a south pole, just like a bar magnet. Now, what happens if we place this solenoid inside another magnetic field, like near a bar magnet or inside a larger electromagnet? Here's what you need to know. It acts like a magnet. The solenoid creates its own magnetic field. So when it's in another magnetic field, the two fields can either Join together if they are in the same direction. Push against each other if they are in opposite directions. It can move or rotate. If the magnetic field around it is not even, the solenoid may feel a push or pull. If the field is even, but the solenoid is turned the wrong way, it might rotate, so it lines up properly with the field just like a compass needle. It can pick up things. This is how electromagnets work, like the ones that lift cars in junkyards. When current flows through the solenoid, it becomes magnetic and can attract metal objects. You've completed this lesson, well done. Test your understanding with these questions, a fun way to reinforce what you've learned. Today, we delved into the concept of electromagnetic field, an interaction between magnetic field and currents. I hope you found the class both interesting and informative. In our next lesson, we'll continue with electromagnetic fields, part 2. Thank you.